Hi there, this is Professor Shannon Gracey. Today we'll be discussing limits at infinity from the Larson and Edwards Calculus text. And if you are interested in using the guided notebook to go along with the lecture, feel free to download it for free at www.mathchick.net. So here we go. Today we'll be looking at determining finite limits at infinity and horizontal asymptotes, if any, of a graph, and then determining infinite limits at infinity. So let's go ahead and make sure our mad limit skills are still there. Warm it on up with the next few problems by evaluating these guys analytically, these limits analytically. And remember, the result of a limit is a y value. Okay? On your mark, get set, go! Okay, let's see how you did. We'll be looking first at this limit here, the limit as x approaches 1 from the right. So with direct substitution, you would get an undefined result. So we basically just need to figure out if we're going to end up with a positive or a negative result, and that will tell us if we're going to positive or negative infinity. So if we just let x equal to, 1.1, which is just to the right of 1, then we would have 3 over 1 minus 1.1, which would be equal to 3 over negative 0.1, which is equal to 3 over negative 1/10, which is negative 30. So this suggests that the behavior of this limit is going to minus infinity. So technically on this one, the finite limit does not exist, right? But what we're going to be looking at is what happens to the graph as we're approaching our vertical asymptotes. And so we are interested in finding out if the graph trends infinitely down or infinitely up at the asymptotes for graphing purposes. Okay, how'd you do? Good. All right, so over here, part B, remember this is a special trig limit. So basically, if you were to multiply this guy by 3 over 3 so that we can match the inside of the trig function, so the angle, with the denominator, we would end up with 3 times the limit as t approaches 0 of 3t over, sine at 3t. Sine at 3t over 3t. So I just multiplied the whole limit by 1, and then I opted to bring in this 3 here is from here, and the other one stayed outside the limit. And what will we get? We'll get 3 times 1, which is 3. How'd you guys do? Awesome. Okay. So limits at infinity. So when we're looking at limits at infinity, we're discussing the end behavior of a function on an infinite interval. So the official definition, and apologize ahead of time, I had all these in boxes here, these theorems in boxes, definitions and theorems, and for some reason they got off kilter in the printing. So this is the definition for limits at infinity. So if you have L as a real number, basically what the first statement is saying is that, hey, the limit as x approaches infinity of f at x to equal to L means that for each epsilon greater than 0, there exists an m greater than 0 such that the distance between the function and the limit is less than epsilon whenever x is greater than m. Okay, so let's think about what this means, right? And then of course we've got this other statement. The limit as x approaches negative infinity of the function equal to L means that for every epsilon greater than 0, there exists an n less than 0, such that the distance between the function and the limit is less than this epsilon whenever x is less than n. So let's take a look at, a picture of one or both of these. So if we have, something like this, and let's suppose that, so x is approaching positive infinity in this one, all right? So if we have, some graph, let's say that we have, I don't know, something like this. And let's suppose that right here we have our L. And then down here we have M. And we have other x values which are greater than m. So basically, you get your limit here, right? Going like this. You have your L plus epsilon. So you basically have these sort of margins of error. And of course, there'll be a better visual in your textbook. But this would be your L plus epsilon, your L minus epsilon. And so what this is saying is, hey, as we keep going further and further this way, our graph approaches this limit here, this finite limit. And it's similar for a picture going the other way. You can have something like, you can even have it sort of dancing around an axis. So you could have something that went, let's see. Well, that's not really dancing around, is it? You could have something that kind of behaves, one way. And then it ends up, as the behavior continues, that it goes to this axis. So if this here, L, was your limit L, notice that at first we're crossing that L. But then as time goes on, let's just say this is L plus epsilon, and then L minus epsilon. But as we get further and further over here, so let's say this is N right here, and then X keeps going this way, you end up getting to that horizontal asymptote, or that limit, okay? So the definition of a horizontal asymptote basically says the line y equals L is a horizontal asymptote of the graph if you get this limit. So you have to take the limit as x approaches plus or minus infinity to find out if you have more than one horizontal asymptote. And if you get a finite result, like 2 or 5 or negative 3, the line y equals that constant, that scalar, would be your horizontal asymptote. Okay, so here's a theorem, all right? This is very important, a very important theorem. So this was a little box for our definition. And then here is our theorem. And this is something you're going to use a lot in Calculus 2, right? Calculus 2. So what we'll have going on here is if you do kind of an example, the limit as x approaches, I don't know, negative infinity of 5 over x squared. From the theorem, our c would be, 5. Our r would be 2. And so because it matches the conditions of this theorem here, that we have a rational number 2, and we have this scalar c, that means that this limit has a result of 0. Okay, so now official definition of infinite limits at infinity. So basically, with these guys, again, there's always a great visual in the textbook. But if you have something that increases without bound, your function values increase without bound or decrease without bound as you go to plus or minus infinity, then you end up getting an infinite result when you evaluate that limit. So, for example, if we're taking a look at something like a graph like this, right? So if we look, as x is approaching infinity, what happens is that there's always some higher y value on the graph that is higher than some value, some arbitrary value of m. So if we have, something like this, where this is n, right? And actually, let's not make it there, where this is n over here, and x is, you're continuing to increase for your x values. And then if you look over here and you have some function value m, right? Then basically, do you see that everything above here, above m, all of these y values, here, all the y coordinates would be f of x greater than that m, right? So that means you're getting this infinite result. And it works the same going on the other side, okay? So, except you're going in the negative direction. So here we go. Let's look at some guidelines that you learned in pre-calculus probably. So, and these are, so basically what happens in this section is this. We are going to learn how to mathematically, well, it's all mathematics, but we're going to learn how to simplify expressions and limits, or simplify functions that you're evaluating the limit of, or the infinite limit of, so that we can use this theorem back over here to justify what the infinite limit is for a function. Now, if there is an infinite limit or a finite limit. Now, when you're doing curve sketching, you can, we're going to have some big curve sketching problems you'll find, and they take a lot of time, so you want to make sure you allow enough time for your homework. And really, 3.6 is, if you end up getting ahead of the videos I'm making, 3.6 is just a culmination of 3.1 through 3.6, with the exception of 3.2. So basically, with what we learn here, you'll be able to do 3.6 as well. When you're curve sketching, you can use these sort of shortcut rules, all right? When you are only asked to find a horizontal asymptote, if one exists, then you have to use the longer way to evaluate a limit. So I'll be clear when we can use which way for purposes of an exam. Okay, so shortcut rules. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function ends up being the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function is plus or minus infinity. Hence, it does not exist. But we often want to know what it is, where it tends towards infinity or negative infinity if we're curve sketching. Okay, so here we go. I'm going to show you the long way of finding these limits, and then we will go from, we'll continue on to some curve sketching at the end. So this ends up being the limit as x approaches negative infinity of 5 over x minus the limit as x approaches negative infinity of x over 3. So I just used the fact that the limit of a difference of functions is the difference of the limits. So here we go. This will give us, using the theorem that we learned earlier, do you guys see that this is the same, x is the same as x to the 1? So if we do a little side work, c is 5 and r is 1. And so this fits that theorem that basically says, if you have the limit as, let me do it in black. If you have the limit as x approaches, I'll just do negative infinity this time, of c over x to the r. So our c is 5 and our r is 1. So that means it's going to be 0, right? So over here, we will have, this would equal to 0, right? Minus, now this guy, do you see, is going to end up being negative infinity. Good. So we end up getting infinity. So officially, the result would be does not exist. Okay? But we have learned that the end behavior as x tends towards negative infinity, the end behavior of our graph is that the function values, the y values, go towards infinity. Okay? All right, so next up we have, so with this guy, what we're going to do is we're going to use that theorem because all we're being asked to do is find this limit. And so what you do is you divide by the x to the highest power of any x that turns up in the denominator, and then you see what it simplifies to be. So here you'll end up with this setup here. And so basically what we're going to do is we're going to divide through by x squared. So we really kind of multiplied the numerator and the denominator by 1 over x squared. And so this will give us the limit as x approaches infinity of Now, remember the x squared is going to divide through both terms. So in the numerator, we're going to have 1 plus 3 over x squared divided by 2 minus 1 over x squared. Now, if you were to split this up a bit, and some of you may see immediately what you would get, but this would end up being equal to the limit as x approaches infinity of 1 plus 3 over x squared divided by the limit as x approaches infinity of 2 minus 1 over x squared. Okay, so I just used that property that the limit of a quotient is the quotient of the limits. And now breaking it up a little bit more, we would end up with the limit as x approaches infinity of 1 minus the limit as x approaches infinity of 3 over x squared divided by the limit as x approaches infinity of 2 minus the limit as x approaches infinity of 1 over x squared. So some of you guys may have recognized earlier that this will yield a result of, so the limit of a constant is the constant no matter what you're approaching. So you'll get 1 for that very first limit in the numerator. And then what's that second one going to be? Good, it'll be 0 because of that theorem we just learned. And then we'll have 2 minus 0 over here. So let's match those up. This limit here was this. This limit here was this. This limit yielded the 2. And then this limit here yielded the 0. So at the end of the day, we would get 1/2, which, as you may notice, is we had an expression inside here that had the same degree, and the ratio of the leading coefficients is indeed 1/2. Okay? All right. So now, here we go. Let's take a look at this one here. And check it out. So using, a similar methodology, if you recall, you can bring the limit inside this root. So we'll have the limit as x approaches infinity of, and what we're going to do is we're going to divide through by x cubed. Okay, so this will be the square root of the limit as x approaches infinity of x minus 1 over x cubed for that numerator, and then we'll have 1 minus 1 over x cubed. So let's move a little faster now. I'm going to be using those same properties so that I used before, but I'm not going to write them all out. So basically, the limit as x approaches infinity of x is going to be infinity, and then we'll have minus 0 over 1 minus 0. Now, it's not super proper to, write infinity in there, but you can serve as a placeholder until you decide whether or not something's going to exist. So at the end of the day, we would end up getting the square root of infinity, which is just infinity. So here the finite limit does not exist. So the end behavior of this graph tends towards infinity as x approaches positive infinity. Okay? All right. So moving along, let's take a look at this guy. So now here what I'm seeing is that, again, I can bring that limit inside that cosine function. Whoops. And using that special theorem, I'll get the cosine of 0. And what is that? Beautiful. 1. Okay. So now for this one, there's a little bit of a trick here. One thing that you're going to want to remember is that the square root of x squared is equal to the absolute value of x, okay? And so you'll just want, this is something that you're going to want to take note of when you're looking at this limit here. So what's going to happen here is that this one will end up being the limit as x approaches infinity of, and we'll have our negative 3x plus 1, and then the square root of x squared plus x. And what we're going to do is basically we're going to be dividing by the square root of x squared for both of these guys. Good so far? Awesome. All right, so then this will end up being the limit as x approaches infinity of negative 3x over the absolute value of x plus the limit as x approaches infinity of 1 over, this would be x to the 1/2, all over, so I'm splitting all the limits again, all over the square root of the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 1 over x. Good so far? Perfect. So now we will get, I'm going to leave that first one alone for the moment. Actually, let's go down to this page so we have room. So we're going to do that first one last. So I'm going to just keep it going. So we'll have the limit as x approaches infinity of negative 3x over the absolute value of x. And then this one will zero out. And then we'll have the square root of 1 plus 0. So we will end up just needing to deal with this limit here. So think about what happens. X is approaching positive infinity, isn't it? And so what's going to happen is if you put in, 100, do you see that you'd have negative 300 over 100? So basically let me write this down, since x is greater than 0, x over the absolute value of x is going to be equal to positive 1. If x was less than 0, we would have gotten a result of negative 1 for that. So what will happen is we'll get negative 3 times 1 over 1, which is negative 3. Now, what would have happened if we had looked at this graph and we had also evaluated the limit as x approaches negative infinity? What would we have had seen? Good. What we would have seen is we would have seen two horizontal asymptotes, one at y equal to negative 3, which we just found, and the other at y equal to positive 3. So let's just take a look at this graph and see what we get. And so what did we start out with? It was negative 3x. See what we had. Negative 3x plus 1 over the square root of x squared plus x. And then I'm just going to graph this one for right now. Well, actually, we can go ahead and graph both of them, the first and second derivative. What the heck? So let's go to Zoom standard. And that's our original function. That would be our first derivative function. And that's our second derivative function. So notice that our second derivative function is positive on the left side, and the original function is increasing. And it's also on this other side, the derivative function is all negative, and notice that we've got a decreasing interval. Right? And then for concavity, both of them are concave upward, so they have positive outputs on the second derivative function. And we have, if we hit trace on our graph, and if we trace left, do you see that our graph ends up tending toward three as we go further? If you look at the y values, you're getting an output of positive 3, like we discussed. And then the limit that we found initially was as x was approaching positive infinity. And as you see, we get to a result of negative 3 on our y values. It's going to take a little longer, but it's trending towards negative 3. Actually, it'll let me move it over. Anyway, you get the idea. We'll end up going, it takes quite a bit longer. See, the x is going towards 20, and we still haven't reached a value of -3 yet for our y value, but you can clearly see that this is our horizontal asymptote as x tends towards infinity. So we'll go ahead and paste that here. All right. So now let's take a look at this problem here. And with this one, what we'll have is the limit as x approaches positive infinity of, and we have an x over x squared minus 1, and if we divide through by x squared, we will get the limit as x approaches infinity of 1 over x over 1 minus 1 over x squared, which is going to give us 0 over 1 minus 0, which is 0. And as you see from our leading terms, the ratio or the degree of the numerator is 1, the degree of the denominator is 2. So the numerator has a degree which is less than the denominator. Hence, using the pre-calculus rules, you would have gotten a result of 0. Okay? All right, so now we kind of get into what we are, looking to find. And I apologize. I'm not sure what happened to my spacing on the notebook, but this is, we'll just have to adapt. Okay, so again, the analysis of these things takes a little bit of time. Just make sure that you don't do all these problems using your calculator only, because it's going to be a two-part exam. One part, there's no calculator, okay? And that's going to be the curve sketching stuff. All right, so here we go. Now, what are all the things that, we had wanted to find on this one? So here, we're going to analyze our graph using all the stuff that we learned. So what are some useful things that we might want to do? Well, we are probably going to need the first and second derivative, right, to figure out extrema and concavity, right? So let's go from there. We're going to need f prime of x. So this f of x can be written as x squared minus x minus 2 to the -1. So f prime is going to be -1 times our something to the -2. Our something is x squared minus x minus 2, and then times the derivative of our something, which is 2x minus 1. Good so far? So f prime at x is equal to -2x minus 1 over x squared minus x minus 2, the quantity squared. Now, finding the zeros of this, we just set the numerator equal to 0 and solve. So 0 will be, I'll just put that negative in with it. So we'll get 2x minus 1 is 0. And we'll get, good, x is equal to 1/2. So our critical number is C is 1/2. Good so far? Awesome. Okay. Now our second derivative is going to be a little more complicated. Why don't we do this? Why don't we, I think it'll be a little bit longer, so I don't think that that we will do it right there. So let's do this. Let's so we found this. So why don't we, so this, what we did first off is we found the critical numbers, right? Now, the second one, let's do our first derivative test, which gives us information about where the functions, on what domain values the function is increasing or decreasing, as well as relative extrema. So if we make our number line, what else are we going to have to consider? We may need to consider perfect, where the vertical asymptotes may be. And so do you see there's going to be a vertical asymptote when? Great, when x squared minus x minus 2 is 0. And this factors as x minus 2 times x plus 1, and set that equal to 0. And we'll have x minus 2 is 0, or x plus 1 is 0. So x is 2, or x is negative 1. And those are the vertical asymptotes. So we need to divide up that interval. The critical number was 1/2. And the vertical asymptotes were at x is negative 1 and x is 2. Right. So we have to test numbers in all these intervals. So how about testing? So for this one, we may want to, make a bigger number line. So this is going from 2 to infinity. This is going from 1/2 to 2. This guy's okay, and then this guy is going from -1 to +1/2, and then we've got an interval from minus infinity to -1. So if we test, maybe -2 can be a test value, 0 could be a test value, 1 and 3 could be test values. So f prime, which we have right over here, at -2 is going to be -2 times -2 minus 1 over. Now, do you see the denominator is always going to be positive? So I'm just going to write over a positive because we just need the sign. So do you see that we'd get a -4 minus 1, which is -5, and then it'd be the negative of that. So it'd be a positive over a positive, so we'll get greater than 0. Now, f prime at 0 is just going to be -1 over a positive number, because that denominator is always positive, which means that this will also be greater than 0. And a lot of times that will happen when you test intervals on either side of a vertical asymptote. Sometimes it's the same sign on both sides. And now if we look at f prime at 1, we would get 2 times positive 1 minus 1 over a positive. And that one, 2 minus 1 would be positive 1, but it would flip to be negative. So you'd have a negative over a positive, so you'd get less than 0. And then at 2, what's going to happen? Well, f prime at 2 will be 2 times 2 minus 1. Whoops, there's going to be a negative on the outside of all that. So we'll have a negative 2 times 2 minus 1 over a positive, which is going to be good. It'll end up being less than 0. So here we go. We have all of our information that we need. Do you see that at x equal to 1/2, there's a relative what? It's going from, at the critical number, it's going from positive, so up the hill to down the hill. So there's a relative maximum. So what else might we need to find? Good. We're going to need to find the ordered pair right where that occurs. So if we look back at our original function, which is just to the left, and we evaluate f at 1/2, we'll find the ordered pair where that happens. So that'll be 1 over 1/2 squared minus 1/2 minus 2, which is 1 over, so that's a quarter minus, I'll just write it out, a quarter minus a half is good, 2 quarters. And then 2 is the same as 8 quarters. So that would end up giving us what? 1 minus 2 is negative 1. Minus 8 is negative 9. So it would be negative 4/9 when you flip it, invert and multiply. So 1/2 comma negative 4/9 is a relative maximum. I'm going to actually say is where the relative maximum occurs. Okay, so we're going to want to make sure we keep that information handy. Let's highlight this guy because we're going to need this for our graph, right? What else might be important stuff? Good. The vertical asymptotes occur here and here at x is 2 and at x is negative 1. What else do we know about our function? What intervals is it increasing on? Good. It's increasing on the first 2 and decreasing on the second 2. So f is, I'm going to say, increasing on minus infinity to minus 1 union minus 1 to positive a half. And f is decreasing on (1/2) to 2 union 2 to infinity. And those are other important things for our graph. Good so far? Awesome. All right, so since we found our vertical asymptotes, we might as well go ahead and find any horizontal asymptotes. Now, since this is part of a bigger problem, you can use your pre-calculus skills. So do you see that the degree of the numerator is 0, the degree of the denominator is 2, so there's going to be a horizontal asymptote at y is 0. And so that's also going to be important stuff for graphing. Okay? Now, let's go ahead and be real careful on how we copy down our first derivative. So f prime at x is negative 2x minus 1 over x squared minus x minus 2, the quantity squared. So now we're going to deal with concavity, right? So we, part of our first derivative test, actually, in order to get all the values for our first derivative test, we actually did this vertical asymptote business second. And then this was all part of the first derivative test information, and then we found, this guy afterward. And so now what we're going to do is we're going to we're going to deal with concavity and points of inflection, POI, points of inflection. So now we need the second derivative. So f double prime at x, I'm going to use the quotient rule. So we'll have 2 is the derivative of the numerator times x squared minus x minus 2, the quantity squared, minus the quantity 2x minus 1 times 2 times x squared minus x minus 2 to the 1 power, and then times 2x minus 1. And this is all over the denominator squared, which will give us x squared minus x minus 2 to the the 4th power. Now, notice that we have one factor of x squared minus x minus 2 in each of the terms in the numerator. So we can divide out one factor of that. Okay. And then now we just need to simplify, because we will need to find any zeros of the second derivative. So this will be negative 2x squared minus 2x minus 4, and then minus 2 times, we have 2x minus 1, the quantity squared will be 4x squared minus 4x plus 1, all over x squared minus x minus 2, the quantity cubed. So f double prime at x will be equal to, let's see, we'll have a negative 2x squared minus 8x squared is negative 6x squared, and then negative 2x plus 8x is plus 6x, and then we'll have negative 4 minus 2 is minus 6. Does this look okay? Looks good to me. All over x squared minus x minus 2, the quantity cubed. So those two negatives will turn f double prime at x would end up being, so if we factor out a negative 6, we'd end up with a negative 6 times x squared minus x plus 1 all over x squared minus x minus 2, the quantity cubed. So that, of course, will give us f double prime at x is 6 times x squared minus x plus 1 over x squared minus x minus 2, the quantity cubed. So finding the zeros, I'll just set them equal to x squared minus x plus 1 to find the zeros. So x is 1 plus or minus the square root of 1 minus 4 times 1 times 1 all over 2. And you see this is imaginary. So there's no real zeros of the second derivative. So what does this mean? Now this problem we'll do on another page. So what does this mean? Well, when we do our test for concavity, we'll just be, again, using the spots where we have the vertical asymptotes. So when x is -1 and when x is 2. So from minus infinity to -1, -1 to 2, and 2 to infinity. And testing that in the second derivative, we can test -2, 0, and 3. So f double prime at -2 is going to be, let's see, 6 times -2 squared minus, I'm looking at that second derivative function up there, minus -2 plus 1 over -2 squared minus -2 minus 2. So this will be what? 4 plus 2 plus 1. So we'll have a positive numerator and a positive denominator. So this will be positive. And then f double prime at 0 will be 6 times 0 minus 0 plus 1 over 0 minus 0 minus 2. So this is going to have a positive numerator and a negative denominator. So that'll be less than 0. And then f double prime at 3 will be 6 times 3 squared minus 3 plus 1 over 3 squared minus 3 minus 2, which will be positive. All right, so what does this mean? It means that f is concave upward on minus infinity to 2 union 2 to infinity, and concave downward on to -1 union 2 to infinity and concave downward on -1 to 2. So we're almost ready to start putting everything together. What about points of inflection? Good, there are no points of inflection. Okay, and then let's see, it's always good to, what was this, number 4, 5? Let's go ahead and, find any intercepts. And so x-intercept, there's none, right? Because the original function doesn't have any zeros. So this would be none. And then the y-intercept would be f at 0 is 1 over 0 squared minus 0 minus 2, which would be negative a half. So we'd have an intercept at 0, negative a half. All right, so let's start making our picture. So no x-intercepts, and then the y-intercept is at 0, negative a half. And now we can make our graph. So here we go. So we had what, x and f at x. We don't have very large numbers, so I'm going to do negative 5 to 5 all around. And we had, let's see, our info. So you just kind of go back and you look, and so we found there were vertical asymptotes at x is 2 and x is negative 1, right? So let's check those guys out. And then we also had a horizontal asymptote at y is 0. So let's draw those guys in. So here's our vertical asymptotes. And then our horizontal asymptote is at y is 0. And then we had our y-intercept was at 0, negative a half. And then remember that we had at 1 and just above negative a half, like at negative 0.45 or something, we had our relative maximum. I'll do that in red, our relative maximum. And if you recall, let's take a look at our concavity and our whether our intervals are increasing or decreasing. So we're supposed to be, in that middle part, we're supposed to be concave downward the whole time. And if you see when we were doing where f was increasing, do you see on the first half of that middle interval from negative 1 to 1/2, we're increasing and then decreasing from 1/2 to 2. So that all fits in with the information about the concavity. So it's going to look, you know, something along these lines. Okay. And then we're increasing from minus infinity to negative 1 and concave upward, and then we're decreasing from minus infinity to or from 2 to positive infinity and concave upward on that last one. So if you want, you can certainly find, you know, a couple of extra ordered pairs to verify your findings. So like if we do f at negative 2, that would be 1 over negative 2 squared minus negative 2 minus 2, which would be a quarter. So it'd be about here. And so that information, you know, combined with the information about where our function is increasing and the concavity, we'd have that graph look something like that. And then how about f at 3? That would be 1 over 3 squared minus 3 minus 2, which is also a quarter. So at 3, we'd be at a quarter. So it's going to be something like this. Okay? And then you can always use your graphing calculator to verify. And so that takes care of this problem. Now we're going to do that next problem on another page. So we'll go ahead and start that next. Why don't you go ahead and pause the movie and see if you can do part B from this example on your own. All right? Good luck. Okay, so for part B, we have h of x is equal to 2x over the square root of 3x squared minus 1. Let me make sure I wrote that down correctly. It's 3x squared plus 1. 3x squared plus 1. Okay, so again, for this one, we're going to do all that fun stuff. So why don't you pause the movie and see if you can do this on your own. Again, don't use your calculator except to check, all right? Okay, so pause the movie, give it a try, see how you do. On your mark, set, go. All right, let's see how you did. So again, what I'm going to do is I'm going to first I'll start out with the intercepts. So our x-intercept is when that numerator zeroes out. So x would be 0. And that y-intercept will actually be the same, but it's a little bit different. It's evaluating h at 0, which would be 2 times 0 over root 3 times 0 squared plus 1, which is 0. So we have 0, 0 for both of these. Okay. All right, so secondly, let's do our asymptotes. Okay. So for our vertical asymptote, or asymptotes, we don't want that. We want that denominator to be greater than 0. So what's inside that radical has to be greater than 0. So that's going to be fine, because if you solve this equation, you'd get 3x squared is -1, which is imaginary. So we'd say none for vertical asymptotes. Okay. Now, horizontal asymptotes, you got to be a little careful on this guy. If you evaluate, first of all, let's simplify. So remember that h of x is equal to 2x over the square root of 3x plus 1. So if we divide through by root x, what's going to happen? Or that was squared, wasn't it? Yeah, it's squared. So we'd be dividing through by root x squared, right? So dividing through by root x squared, dividing through by root x squared. Actually, that's already under the root. So now h of x is going to be equal to 2 times x over absolute x in the numerator, and then over the square root of 3 plus 1 over x squared. So do you see that when I evaluate the limit as x approaches positive infinity of this, I will get positive 1 for the x over root x. And so I'll end up getting 2 times positive 1 over root 3, which is 2 over root 3. And let's get an approximation for that. So that's approximately 1.15. And then now the limit, though, as x approaches negative infinity of this is going to end up being equal to 2 times negative 1, because you plug in a negative x value, you get a negative in the numerator and a positive in the denominator. So that simplifies to negative 1 over root 3. So that'll be approximately negative 1.15. So our horizontal asymptotes are at y equal to plus or minus 2 over root 3. Good so far? Awesome. So let's just we've got a horizontal asymptote, don't have a vertical asymptote, and then our intercepts. X-intercept is the same as the y-intercept, which is at 0, 0. Cool. All right, so now let's go ahead and, what is that? 1, 2, 3. Let's go ahead and do the first derivative test. So we're going to find the critical numbers. So we need to find h prime at x is. So we'll get 2 times root 3x squared plus 1 minus 2x times the inside derivative is going to be 6x's. We'll have a 1/2 times that, and then it'll be over root 3x squared plus 1. And that's all going to be over root 3x squared plus 1, the quantity squared. So h prime of x is going to be, let's see what we have. So the 2's divide out. So we'll get something along these lines. We can factor out a 3x squared plus 1 to the negative 1/2. And we'll have in the numerator 2 times 3x squared plus 1 to the 1 power. And then we'll have minus 6x squared all over 3x squared plus 1. So now h prime of x will be, we'll drop down that 3x squared plus 1 to the negative 1/2, and that'll give us 3x squared plus 1 to the 3/2. And then in the numerator, we'll have 6x squared plus 2 minus 6x squared. So h prime of x will be 2 over 3x squared plus 1 to the 3 halves. So there's no critical numbers, right, for that. So there's going to be no relative extrema. But we can certainly figure out, on which intervals our function is increasing or decreasing. So if we do a little test, let's see. Basically, we had no critical numbers and we have no vertical asymptotes. So you test any number that you want in the interval. And I think what you'll see is that this is increasing the whole way. So if we just choose 0 to test, we would have h prime at 0 is equal to 2, which is greater than 0. So h is increasing on minus infinity to infinity. So that'll be helpful for our graph. Okay, so now the next step is going to be dealing with concavity and points of inflection. So what was our derivative again? H prime of x was 2 over 3x squared plus 1 to the 3 halves, which we can write as 2 times 3x squared plus 1 to the negative 3 halves. And so h prime, double prime of x will be equal to 2 times negative 3 halves times 3x squared plus 1 to the negative 5 halves times 6x, using the chain rule. So h double prime at x will be equal to, the 2's will divide out here. So I believe we'll get negative 18x over 3x squared plus 1, which is always positive, right, to the 3 halves. Because you're squaring your x values, multiplying by a positive 3, and increasing it by 1. So that denominator is always positive, right? So if we set this equal to 0, then we get x is 0, and that's one of our test values. But don't forget, if we had had any vertical asymptotes, then we would have needed to test those as well. But we didn't, so we're just testing 2 intervals. So this one looked like a much harder problem, but it's not as bad as that first monster. So let's see, h double prime, why don't we do negative 1 and 1 as test values? So h double prime at negative 1 is going to be negative 18 times negative 1, which is greater than 0. And then h double prime at positive 1 is negative 18 times positive 1, which is less than 0. So there will be a point of inflection at 0. So I think, and so that's going to be, remember, at the origin, right? Yes. So there's a point of inflection at 0, 0, and H is concave upward on minus infinity to 0 and concave downward on 0 to infinity. So these are all useful items. Okay, so now I think we have enough to make our picture of our graph. Let's see what we've got. Okay, so the numbers that we're working with are what? We've got pretty small numbers, so I think I'll do plus or minus 5 again on our grid. Okay, so we've got 5, negative 5, 5, negative 5, x, h of x, and at plus or minus about 1.2-ish, we had horizontal asymptotes. Okay, and then remember that our graph is increasing on its entire infinite domain, and then we've got it concave upward from minus infinity to 0 and concave downward on 0 infinity. So our point of inflection and intercepts are at 0, 0. So I'm thinking that it's going to look like this. Something like this. Okay, and you can verify it with the graphing calculator. Okay, so that was a heck of a lesson, right? Just remember that 3.6 is just more of this. You're just basically doing more graphs, more curve sketching by hand. And so have a great day. Bye.